Hello everyone, welcome to IFS Seminar. It's the first seminar of 2025 and also seminar number 25. And we are happy to have Maxwell Hutt today, who will talk about generalized symmetries, anomalies, and Boltzmann modes. I have a privilege to work with Max in the same group at Imperial, and I'm happy to see his talk and finally learn more about his recent work.
Thank you very much. Thanks, Garabet. So I'll also thank the other organizers. I'm very happy to be invited to be talking today. So I want this to be interactive. Please interrupt me as often as you would like. It'd be great if this was a conversation rather than a lecture. So I'm going to talk about some work that came out last year with Chris Hull and Ulf Lindström. There were a set of papers. I'm going to focus primarily on this middle one here. And hopefully, time permitting, I'll talk a bit about the others as well. So I'm going to start. I intend to spend a good bit of time talking about some background and generalities, and then about details later on. The context within which this work sits is a very old question, which is how symmetries in general tell us about physics and what we can learn about physical theories and nature through them. So there's obviously mass of literature about this theme, and I'll highlight a couple of classic results that will be important for us. So the first of which is the Landau paradigm. So this is the idea that you can classify different phases of matter by not just the symmetries that they have, but the way in which they manifest them. So they could, for example, be spontaneously broken, or they could be preserved by the particular phase. And secondly, of course, the Goldstone theorem that we'll all be familiar with, which is telling us that if we have spontaneous breaking of symmetries, then we should expect massless modes in the spectrum. So in both of these cases, we're learning something about the physics, either the particular phase or the presence of some particular modes because of some symmetry artifact in the theory. So more recently, by which I mean in the past sort of 50 years, an important consideration in this type of question is the presence of Hooft anomalies. So I'll talk in detail about Hooft anomalies in a second, but what we should think of them as is a property that a global symmetry can have, which means that it cannot be gauged. So it's not telling us that the symmetry gets broken by quantum effects, like one might normally associate with the word anomaly, which appears to mean about 20 different things in the literature. But in this case, an anomaly is not telling us that a symmetry is broken. Rather, it's a good symmetry. The theory is not sick. It's just a good global symmetry, but it cannot be gauged. So arguably the most important feature of these anomalies is that they are RG invariants. They have that property, and as a result, if I find a UV theory with some global symmetry with a Hooft anomaly, then as I undergo RG flow, in the infrared, I must be able to match it, provided that the flow preserves the symmetries. And oftentimes that will give strong constraints on the possible infrared theory that could describe this system. So obviously, in general, describing the infrared of an RG flow given a UV starting point is a very difficult problem, and sometimes this can give you some sort of data that theory must satisfy some constraint. Good. So let me talk a bit about Hooft anomalies in general. So the setup is to consider some field theory with a global symmetry, which I'll describe by some group G. And in general, given a global symmetry, you can couple background gauge fields for the symmetry. I'll denote them by B. So the path integral with those couplings inserted is going to be Z of B. And what B is in particular depends exactly on what G is, whether this is a continuous or discrete symmetry, whether it's a group symmetry, there's higher form symmetries and so on that I'll go to discuss in a minute. But in general, there should be some notion of a background gauge field you can couple. And being a gauge field, it will have some gauge transformation. So I'm going to denote them in general like this. So lambda is the parameter of this gauge transformation. This will take some form. Good. So what you might hope for is that the path integral, once I've coupled B, is gauge invariant under these background gauge transformations. And then you would say that you have gauged this symmetry. That's what it means to gauge a symmetry. But that, of course, is not always possible, unfortunately. And in general, what can happen is that as I do a background gauge transformation of B, I could pick up not quite Z of B, but it up to a phase. This phase that I pick up, this alpha, is what we call the anomaly. So this is the Hooft anomaly. Importantly, it's a local functional, not just of the background fields, but also of the gauge parameter. Okay, so this is the general case. And if this is such, then obviously we can't achieve this goal of effectively gauging the symmetry. Good, so there's one subtlety that's important and needs mentioning, which is that in general in quantum field theory, exactly what the path integral is as a function of the background fields is slightly ambiguous, and it depends on your choice of a regularization scheme. So you impose some UV cutoff, or you do dimensional regularization, or whatever your favorite scheme is. But doing so will introduce some dependence on the cutoff. And the job in life of counter terms is to remove that ambiguity. So you can safely remove the regulator. So introducing counter terms, in particular, some of these counter terms will depend on the background field B. And so under a background gauge transformation, they will vary in some way. So if I choose different counter terms to be included in the path integral, then the way in which they vary will influence this alpha, this anomaly. So the anomaly in itself isn't a well-defined object, but the anomaly up to the variations of possible counter terms is the real object that defines the anomaly. So in particular, if I give you some quantum field theory with a global symmetry G and ask you, does it have a Hooft anomaly, you need to solve two problems. Firstly, you need to find how do I couple a background field to gauge the symmetry? And then if it has a Hooft anomaly, can I add counter terms which cancel the anomaly? Okay, and if you can't, then it genuinely has a Hooft anomaly. So there's a slightly more refined notion of Hooft anomalies that I'll need, which is that of a mixed Hooft anomaly. So this is in the following setup. You have two global symmetries, so two groups, G1, G2, and I'll couple backgrounds for both of them. And it can be the case sometimes that if I turn off one of the backgrounds, for example, I turn off B2, then I do a background transformation of B1, there's no problem. I don't pick up an anomalous phase. And the same is true the other way around. If I turn off B1, then I can freely do transformations of the B2 background field. So individually, the symmetries do not have a Hooft anomaly. But what can happen is that if I turn on the background for the second symmetry, B2, then doing a background gauge transformation of B1 picks up an anomalous phase. So I only see this anomaly when I have both backgrounds present. Okay, so then we would say it's a mixed Hooft anomaly. So an example to have something to hang off of, a 2D compact boson, for example, very common theory that pops up all the time, has two U1 symmetries, momentum and winding, commonly referred to, and they also have a mixed Hooft anomaly of this form. So individually, they're not anomalous, but you cannot gauge them simultaneously. That's how you should interpret a mixed Hooft anomaly. So let me expand a little bit on the importance of these Hooft anomalies for fixing the infrared of some phase. In general, if I take some UV theory and I undergo a renormalization group flow, I'll end up eventually at a scale invariant fixed point in the IR. And that fixed point, broadly speaking, falls into two categories. It will either be gapless or it will be gapped. Gapless meaning that there's no energy gap between the ground state and the first excited states, and gapped meaning that there is a gap. And a gapless phase will be described then by a conformal field theory, whereas a gapped phase will flow in the infrared to a topological theory. And in either case, that fixed point can either preserve the symmetry or it can spontaneously break it. So by spontaneously breaking, we mean that the vacuum transforms non-trivially. And so if the RG flow preserved the symmetry that I had in the UV, then as we said, the fact that Hooft anomalies are RG invariant means the IR must match it. And oftentimes that can give you some constraints. So these constraints generally go under the name of LSM type theorems, referring to an original work of Liebschulz and Mattis. Sometimes in anomaly enforced gaplessness. There are many names for these things, but this is the general sort of strategy. So let me mention a couple of examples. If you start with a chiral anomaly, which we're all familiar with, so for example, take 40 fermions, you have vector and axial U1 symmetries, they share a mixed Hooft anomaly, and you can derive just from the presence of this anomaly that there is a gapless mode in the spectrum. So in this case, it's very strong constraint in the IR. You can eliminate half of the possibilities in the way that I framed it here, so you know you're ending up in a gapless phase. More recently, attention has been given to discrete symmetries, and it was shown that there are certain types of discrete anomalies, so Hooft anomalies between discrete symmetries, which cannot be matched by topological theories which preserve the symmetry. Okay, so if you had some UV theory which started off with an anomaly of this kind, then you know that it cannot end up in a gapped phase which preserves the symmetry, i.e. it cannot flow to a topological theory that preserves the symmetry, because these symmetry preserving TQFTs are incapable of producing such anomalies. So in that case, it doesn't tell you what the IR theory is. It doesn't tell you whether it's gapped or gapless, but it does tell you that it is not a symmetry preserving TQFT. So there's some constraint at least. So a good example is SU2 Yang-Mills with a theta angle set to pi. So the other ingredient in the work I'll talk about today is a new notion of what symmetries should be in quantum field theory. So in a paper that's is just gone, just past its 10th birthday, there is a new notion which tells us that global symmetries in quantum field theories should be associated with the existence of some topological operator. Okay, so a topological operator is some operator supported on a submanifold of the spacetime, and the operator is, so any correlation function with this operator inserted does not depend on smooth deformations of the submanifold that I define the operator on. Okay, so in that sense, the operator only cares about the topology of the submanifold it's on, so it's a topological operator. Good, so this includes the previous notion of what you always would have called a global symmetry, and many more things. Some of those extra things are so-called higher form symmetries. These will be very relevant to what I'll talk about today. So higher form symmetries come about when you consider topological operators which have higher codimension. So you could consider a topological operator of any dimension in general, and they act naturally on objects of different dimensions. So these higher form symmetries act in general on extended objects rather than on local operators, as we're familiar with in normal discussions. You also have what are called non-invertible symmetries. So this sort of definition of a symmetry in terms of a topological operator makes no reference to a group. So in particular, you can have topological operators which fuse according to a more general type of structure than a group. There's a lovely description of these in terms of category theory. So I won't use these today, but I just want to highlight that there's almost all standard notions of what we might call a symmetry have probably gone out the window in the past 10 years, and there's a beautiful story beneath them. Good. So within the context of what I described before, the natural question to ask is, given this more general notion of what I should call a symmetry, can I discuss, for example, Hooft anomalies of these generalized symmetries, and do they tell me anything new about this method that I described to constrain the infrared of RG flows? And indeed, there's been lots of work in that direction. A particular example that I'll highlight now and we'll review in detail in a second is the following. So a theory with a mixed anomaly between two U1 symmetries, a one-form U1 symmetry. In this talk, a superscript will denote the form degree of a symmetry. So a U1 one-form symmetry and a U1 D-3 form symmetry. A Hooft anomaly between these two of a particular type is enough to derive the presence of a gapless mode in the spectrum, and that it's spin 1. So a massless spin 1 mode you would normally call a photon, and so you can view as a result the photon as a type of Goldstone mode whose masslessness is protected by this particular anomaly. Okay, so you don't need to write down the Maxwell action to derive to describe a photon. You can tell me you have a theory with these two symmetries, and they have this mixed Hooft anomaly, and then you must have a graviton, have a photon as a result. So I'll review exactly how this story works in detail in a second. But the novelty that I want to point out in this talk is an extension to other massless fields. So it's natural to ask, if I can view the photon as a Goldstone, can I do the same, for example, for a graviton or for tensors in other representations of the Lorentz group? And we'll see that the answer is yes. There are many subtleties associated with it, and we'll attack them in turn. Good. So the outline for today, as I say, I'll review how we see the photon as a Goldstone, how that sort of idea can be extended to the graviton. Hopefully, time permitting, I'll discuss a bit about other symmetries that the spin 2 theory, the graviton theory, has, and then I'll wrap up. Good. So this is probably a good point to stop for any questions, if anyone has any. If not, I will carry
Sure.
on.
Can I ask about this example about 4 slides back where you talked about the mixed anomaly between momentum and winding?
Of
It's
course
just
you
wondering
can.
if you could just go through that example. Say, for example, yeah. So, for example, what's B1 and B2 in this case?
Good. So you can couple. So the momentum symmetry of a compact boson is essentially just a shift symmetry. So this is a periodic scalar, and I can shift that scalar by a constant. Okay, and you can gauge that constant shift by introducing a one-form gauge field that transforms just like a Maxwell field in the normal way. The winding symmetry is also a U1 symmetry, and you can gauge it by introducing a different one-form gauge field. It's slightly more subtle because this is the winding symmetry is what you might call a magnetic or a topological symmetry, but nevertheless you can couple a one-form gauge field in the way that I described above. So in that case, B1 and B2 are both normal one-form gauge fields,
So, what is the
U1 gauge
winding
fields.
symmetry? I mean, how's it act or what?
So the winding symmetry doesn't act on the scalar in the in it. So I'll describe in detail something that's very analogous, so we can return later if it's unclear. But it's a sort of topological symmetry telling you about how the scalar wraps the S1 rather than a particular, say, shift symmetry of the scalar. So it doesn't act in an obvious way, but nevertheless you can define, in the language of generalized symmetries at least, you can define a topological operator based on this symmetry. And so in the new language of generalized symmetries, you would say that this is a good global symmetry.
So
Oh,
you can
okay.
say that it's the shift symmetry of the dual of the scalar.
Absolutely. So what is something we'll discuss at length is dual representations of these theories, and in the S dual language, the winding is a shift symmetry of the dual scalar.
Oh, okay, but then it does have an action on the scalar, no? I mean, you could get
But
it
not
just
on
by
the
following.
originals. So in each language, so in the if you write the theory in terms of the dual scalar, then the momentum symmetry becomes sort of topological in this way, in that it doesn't have an obvious action on the field in the theory. So you always have
Well,
one of them acting in the sort of obvious way and one of them not.
if you shift the dual scalar, that also changes the scalar, right? It's non-local, but it should still change this.
Well, they're related by a derivative. So if I shift the dual scalar by a
Okay.
constant, the original scalar doesn't see it.
Ah, it doesn't change at all.
No, so they're
Okay.
related, but a derivative of the original scalar is related to the Hodge dual of a derivative of the other scalar. So they're
Yeah. Okay.
non-local in
Oh,
that
so
way.
so you're not. So d of star phi doesn't change. You're shifting star phi without changing d of star phi.
Yeah, exactly. So yeah, so
Oh, I get it.
it's true
Okay.
that in either language, phi or whatever you call the dual field, one of them acts like a shift and the other doesn't. But
Okay.
you can understand how to gauge the winding symmetry by gauging the shift of the dual, for example.
Okay. Thanks.
Okay, very
Yeah,
good.
but these statements are dependent on the formulation or not? I mean, if I write a formulation where this both the field and its dual are present as fundamental fields, would that help to gauge both without creating a
Yeah, you could.
anomaly?
No, you'll find the in any duality frame, you'll find the anomaly. You'll find the anomaly. So it's entirely analogous to this example that I'll go through in detail about
Yeah,
the
yeah.
photon.
Okay. Mhm.
It's essentially the same thing with fields of different ranks. But yeah, you'll always see the anomaly.
Mhm.
Okay. Any other questions, or shall we proceed? Okay. So let's start with the Maxwell theory then. So just to fix notation, we have a one-form gauge field A. It has a normal gauge invariance. The curvature of the U1 bundle I'll denote by F, and the standard Maxwell action takes this form. Good. So the equation of motion of the free field is just that F is co-closed, and there's a Bianchi identity that F is closed. So I can define now a two-form current, which is just proportional to F. I'm just choosing constants in a convenient manner, but it's proportional to F, and it's conserved, co-closed, only on the equations of motion. And quantities that are conserved on the field equations in a given theory, we would normally call electric. So I'll refer to this as the electric symmetry. You can also see this as the Noether current associated with a shift of the gauge field. And I can shift the gauge field A by some one form lambda, provided that lambda is closed. Okay, if I do that, then F obviously doesn't change and the action is invariant. In particular, I need to shift it by a lambda which is not exact, otherwise this would be a gauge symmetry. So the global part of this symmetry are those lambdas which are closed but not exact. So they're labeled by cohomology. Good. In particular, just to relate this back to what I was saying about generalized symmetries, given this current, I can form a topological operator by integrating its Hodge dual over a codimension 2 cycle. And it follows from the conservation of the current and Stokes' theorem that this Q does not depend on smooth deformations of sigma. Good. So there's another symmetry which is related to a current which is the Hodge dual of F. And this is conserved, i.e. co-closed, identically from the Bianchi identity. So this is not just on the field equations. Quantities that are identically conserved you would normally call magnetic, sometimes topological. And in particular, because the current is identically conserved, it cannot be the Noether current for any transformation of A. Noether currents are only conserved on the field equations. Okay. But, so you may ask, like, well, if there's no transformation of the fields which leads to this current, then why should I think of it as a symmetry? Well, in the generalized symmetries language, you can do exactly the same thing as before. You integrate the Hodge dual of this current over a 2 cycle, and this Q also defines a topological operator. Okay, so conservation of the current and Stokes tell you that this is not dependent on smooth deformations of this 2 cycle. Okay, so in the generalized symmetries language, it's clear that both of these are symmetries. If you don't want to call them both symmetries, you don't have to, but I will. So convention is that this one on the left, this one that I call electric, is a so-called one-form symmetry. So it acts naturally on line operators. That's because the operator that I formed in this manner is codimension 2, and so in d dimensions it links naturally with a one-dimensional operator. And analogously, the magnetic symmetry here is defined on a 2 cycle, and so it links naturally in d dimensions with a d-3 dimensional operator. So again, they're just names. I'm not going to dwell on the nomenclature of this generalized symmetry stuff, but I will use the conventional names. So let's talk then, just like what we were doing for the compact scalar, about the dual formulation and how these symmetries look. So Maxwell theory has a dual formulation in terms of a d-3 form gauge field in d dimensions. It again has standard gauge transformations, and the curvature of the gerbe is labeled here by F tilde. And the duality is imposed by the fact that F tilde is related to F by a Hodge dual. Good. In particular, in the dual frame, the equation of motion is that F tilde is co-closed, and the Bianchi identity is that F tilde is closed, which are swapped with relation to what they were in the original formulation in terms of A. So now if I look at the one-form symmetry, which was associated with the current JE, it is now, if I write it in terms of A tilde, conserved identically. And so I would say it's magnetic. In particular, it is not related to any transformation of the field A tilde. Whereas the d-3 form symmetry is now only conserved on the equations of motion when I write in terms of the dual field. And so I would say it's electric. And it can be seen as a Noether symmetry associated with shifts of A tilde. Okay, so we learn, as I'm sure is familiar, that magnetic symmetries and electric symmetries are interchanged under this duality. Of course, it's called electromagnetic duality for a reason. Good. So we have a theory with 2 different global symmetries. And we should ask whether they have Hooft anomalies. So in particular, we need to learn how to couple background fields. For the one-form symmetry, which was a shift of A, we add a 2-form background field. Okay? And that 2-form background field is going to have a gauge transformation looking like this. And that is convenient because it means that the combination F minus B is invariant for arbitrary lambda, which now doesn't need to be closed. So F is dA, so F shifts by d lambda. B also shifts by d lambda, so they cancel. Good. So then I can gauge the theory by just taking the action and replacing F by F minus B everywhere. And so this will now be invariant under these 2 transformations for arbitrary lambda. Good. So you can gauge the one-form symmetry. The d-3 form symmetry, similarly, we need to couple a background field. This time, as there was no transformation of A which led to this symmetry as an Noether symmetry, we don't have a transformation of A that we need to consider. Rather, the background field transforms in some way that we define. And I gauge the action as follows. So I have the normal action, and then I add a second term which couples F and B tilde. So if you wrote this out explicitly, this looks like the magnetic current Jm fully contracted with B tilde. So it's the normal linear coupling to an earther current that you would put. So you just contract the current and the gauge field. Good, and you can check that under this transformation of B tilde, this is invariant up to boundary terms, which so I'll assume the field drops off fast enough to neglect them, or you put this on a closed manifold, and then it's exactly invariant. So you could again protest and say, well, I didn't have any transformation of the field that needed gauging. So what do you mean you've gauged the field? Well, in the Joule formulation, the D-3 form symmetry was associated with a shift of A tilde. And if I do a gauging in the Joule formulation, analogous to what I did on the left here, and then write it back in terms of the original gauge field, I find exactly this action. So if you want to take that approach, you can. In any case, I've coupled the background field in a way that gives a gauge invariant action. So I would say I've gauged the symmetry. Good. So neither of these symmetries have a Hooft anomaly individually. I can successfully couple background fields and the action is invariant. But we should ask then, is there a mixed anomaly? Okay. So we need to couple both background fields. Let's do the most naive thing and just add the two contributions that we considered before. So in the first term of the action, we replace F by F minus B. And then we add in this extra second term that was trying to gauge the Joule symmetry. So we ask, is it invariant under both of these transformations simultaneously? Well, consider the second one first. The first term of the action doesn't depend on B tilde, so obviously it's invariant. And the second was invariant by construction, so tick. The first one, on the other hand, has the following issue. The first term is invariant by construction, but the second term, if I shift A by lambda, picks up a term which does not vanish. So this action is invariant under the second, but not the first. I could try and fix things by replacing F in the second term by F minus B. And if I do that, then this is all manifestly invariant under the first transformation. But now if I do the background transformation of B tilde, I get a contribution from this new term over here, which does not vanish. Okay, so again, we have gauged one, but not the other symmetry. And you can convince yourself that there is no possible way to gauge both. So there's no way to put both background fields in the game in a way that the action is invariant under both of these transformations. So this is exactly what happens for the compact boson as well, just with more indices in this case, but all the terms that arise are completely analogous. Good. So we've derived then the presence of a mixed Hooft anomaly between these two symmetries. So what's that useful for? What's the point? So let me remind you, in the original theory, then we had these two symmetries. Their currents were proportional to F and its Joule, and they were both conserved. Good. Now let's look in the theory where I have gauged the shift of A. Okay. So in that theory, it doesn't make sense anymore to consider these two currents because they're not gauge invariant. Okay. So in this theory where this shift is gauged, then any operator that I consider should be gauge invariant under this shift if it's meant to be a gauge symmetry. However, if I shift A by lambda for some lambda which is not closed, then F is clearly not invariant. So instead, I should consider these improved currents where I replace F by F minus B. So these are manifestly gauge invariant. I'm calling them bold J's. And in the gauge theory, they have the property that the electric one is still conserved, but the magnetic one is not. So in particular, if I have gauged the one form symmetry with a background field B, which is not flat, then the magnetic symmetry is broken. Okay, so what we see is that gauging the one form symmetry, in this case, the shift of A, breaks the D-3 form symmetry, the magnetic symmetry, explicitly. Okay, which is another hallmark of a Hooft anomaly. Gauging one breaks the other. So now we ask, as was first considered in these works here, what does this tell you about the quantum theory? So we have these two conservation equations, or non-conservation equation in this case, and we should impose them in the quantum theory as Ward identities. So let's try and impose these two relations as Ward identities. Here, I've written them explicitly with indices here, just to make sure everything's crystal clear. So the strategy will be the following. Take these Ward identities and functionally differentiate with respect to the background field B. Now, if I do that on the right-hand side here, I'm just going to get a number. And I'm going to write things in momentum space so that derivatives will become momenta. But on the right here, I'll just get a number. And on the left, I'm taking a functional derivative of this correlation function. And I know that in the action, when I did the gauging, the current couples linearly to the background field, just like it normally would for a normal coupling of a background field. So if I take a functional derivative with respect to the background, I'm just going to pull down another copy of the current into the correlation function. Okay, so I'm describing with words what you do, but in detail, it is the following. So we're going to consider the following correlator. It's a correlation function between the two currents, JE and JM. I'm writing here the Hodge rule of JM just so it has fewer indices, just to make life simpler. And I'm writing it in momentum space. Now, Lorentz covariance fixes its form up to two arbitrary functions, C1 and C2 here. So you can have fun writing down all the possible contributions and seeing which of them can contribute. And you'll find that it's only these two. Now what I do is I take the Ward identities that I wrote on the previous slide and I functionally differentiate them. And in the manner that I described, I get two constraints. One of them is this, and the other one has, as I said, just a number on the right-hand side. And if you impose these two constraints on this correlation function, you will fix C1 and C2. And so you can derive exactly the form of this correlation function between the two currents, and the answer looks like this. Okay. In particular, this answer has a pole at p squared goes to 0, and a pole in a correlation function tells you about the presence of a massless mode. If it's, well, in general, because about the presence of some mode, but here it's massless. Good. So a couple of comments. Firstly, we discussed before that you could add counter terms in different ways. I can choose different ways to gauge the symmetry by introducing counter terms that involve the background fields. And that would change the presentation of the anomaly. That was what we discussed at the beginning. If you do so, then what you will find is that only changes this discussion by counter terms. So in momentum space, counter terms are terms that are analytic in P. So in particular, you can make this contribution go away, but you cannot change the singular part of this correlator. Okay, so the presence of the pole here is robust. You can gauge in any way you want, but that will always be there. And secondly, you can derive from this the fact that the massless mode is a spin one particle. So this follows from some nice representation theory results of Weinberg and very soon after Dissler a few years ago. So you can derive very literally the presence of a photon, a spin one massless mode, just from the anomaly. So that brings us to the first major conclusion, which is that you should view the photon as a Goldstone mode, and it's massless because of a mixed Hooft anomaly. Okay, so I'm using the word Goldstone here in a slightly more general context than it normally is. I'm not making explicit reference to spontaneous symmetry breaking. Rather, I'm referring to the fact that this is a massless mode coming from a particular symmetry structure. Good. So the critics will say, you started with Maxwell theory and you derived a massless spin one particle. I think I knew that before. And I would say, yes, of course you did. But in fact, what I really showed you was that the presence of this massless mode comes directly from the anomaly. So I didn't need to write down the Maxwell action at the start and show you this full thing. I could have just said, here are a pair of Ward identities that describe a mixed Hooft anomaly, and then you would derive the presence of a photon. Okay, so it's not just Maxwell theory that has this property. And if I deform the Maxwell theory in any way which preserves these symmetries, then everything I said will remain true. Okay. Good. So I should mention in passing some other work where you can also see the photon as a Goldstone more explicitly by studying spontaneous breaking of this one form symmetry from a tangential perspective. Okay, good. So hopefully that has clarified any doubts that we had before about the photon case. So I now plan on discussing the graviton theory and the analogous comments for the graviton. If there are any questions at this point.
Okay, so I'm trying to understand what kind of object this B is. So B should be a gauge field for this one form symmetry. So I would think it would have some sort of field strength, which is some kind of a 3 cocycle or something. But then you just started talking about B minus F, which, I mean, so B itself wouldn't be globally defined if you had some H, which was non-trivial. But then B minus F, I mean, you seem to be treating it as if it's something which exists everywhere.
Yeah, this is a fair point. So that's not true. So B indeed is a two-form gauge field. It has some field strength, and B in general could be non-local. F, of course, is globally defined, and I'm adding and subtracting them as if they were the same type of object. That's not quite true. So in general, one would need to do this patchwise and be careful about such things, which I haven't included here. There's an understanding of this anomaly in the sort of differential cohomology language as well, in a nice work by Yuji Tachikawa and someone else from a few years ago. So though I won't be able to recite the details of that on the spot, it's my understanding that there's a good treatment of how to deal with such matters in the literature.
Oh, okay. So if you can understand the mixed anomaly patchwise, somehow you can lift that to the whole thing, is the claim.
That is my understanding.
Okay, thanks.
Thank you for the question. Very good. So if there aren't any others, we'll proceed. So I'm going to talk now a bit about the graviton theory, just on a flat background. So this is a theory of a gauge field, which is a symmetric two-tensor. So it has a Young tableau labeled like this, with the normal linearized diffeomorphism gauge invariance. So an important object in the discussion now will be this gamma, which is a linearized version of the Christoffel connection. It's not literally the linearization of the Christoffel connection, but it is up to a gauge transformation. So it's one derivative on H, anti-symmetrized in this way. And importantly, it is not gauge invariant. Okay. The object that is gauge invariant is the linearization of the Riemann curvature, which is two derivatives on H skewed in this fashion to give you a 2-2 type tensor. So I'm introducing some notation here on the right in gray for those of you that hate indices like me. So I've got a DL and a DR. So DL is an exterior derivative acting just on the left index, and DR is one acting on the right index. Okay. So the natural free field equation in 4 or more dimensions is that the linearized Einstein tensor vanishes, and you can get that as a field equation from the following action. So I'm again assuming fields are diagonal fast enough to neglect boundary terms, and so if you do so, then this is equivalent to the massless Fierce-Pauli action that you get from just linearizing Einstein-Hilbert. Good. So we are again looking for a pair of dual symmetries, and much like one of the symmetries in the Maxwell theory was a shift of the gauge field, we'll here study a shift of H. So if you do this shift, you'll find that it's a symmetry of the action that I wrote on the previous slide, provided that alpha obeys some constraint, which is that if you pretend alpha is a gauge field and make the Ricci tensor out of it, then it needs to vanish. So for example, alpha could be a constant. That would be the simple case. The fact that there's a constraint on alpha is telling us that this is a global symmetry, and gauging it would mean removing this constraint, just like we did before. Good. So this is a global symmetry. It's continuous. So there's a Noether current. The Noether current takes this form. So I'm writing bars in the indices to separate anti-symmetric ones. So mu and nu here are anti-symmetric, and then rho is separate. Okay. Just to keep an eye on the representations. So the Noether current has this particular form. It won't be very necessary for what follows, but the important thing is that it's a function of gamma. Okay. And you can explicitly verify that the divergence of this J on the first indices vanishes on the field equations. And so we would call this an electric symmetry. It's only conserved on the equations of motion. So this divergence on the left, I'm going to denote as a DL dagger. It's a D dagger on the left only. Good. So the dual symmetry is one which corresponds to this current that I'm denoting J tilde. So it has D-2 anti-symmetric indices, and then another one. And it's essentially given by contracting the epsilon symbol with gamma, with the linearized connection on the first two indices only. So that is a left Hodge dual of gamma. Okay, I think this is easier to follow than the mess of indices over here. And again, you find that if you take its divergence on the first index, then it vanishes identically. And so we would call this a magnetic symmetry. Good. So a fact, as I mentioned, that will come back to bite us is that these currents are not gauge invariant. Okay, so let's bear that in mind. So I'm calling them a 1-1 biform symmetry and a D-3 1 biform symmetry. This is an analogy to the Maxwell case where we had a 1 form and a D-3 form symmetry. For the 1 form symmetry there, was related to a shift of A by a one-form parameter. Here I'm shifting H by a parameter which is in a Young tableau, which is labeled by 1, 1. So it's got 2 columns, 1 box in each. So I'm calling this a 1, 1 biform symmetry. Again, just a name, but that's what I'll refer to. Good. So I've introduced these 2 symmetries. The second one, again, has a current which is not associated with any transformation of the gauge field because the current is conserved identically. So one should ask, what on earth is this current telling me? Is it a random thing, or is it something meaningful? And so I'll describe quickly the notion of gravitational duality. So let's recall that for the one form gauge field, we had a dual gauge field in the d-3 form representation of GLD, and the duality was imposed up to some prefactors by F and F tilde being Hodge dual. Similarly, H, this 1, 1 gauge field, has a dual description in terms of a gauge field in this representation of GLD. So there's d-3 boxes in the first column and 1 in the second. The gauge invariant object that you build out of D, again, has 2 derivatives acting on D, which are skewed in a particular manner, dl, dr, d, to build a d-2 object. And the duality is imposed by setting this S, the field strength of D, equal to the Hodge dual of R on the first indices. So R was the curvature of H, the original graviton, S is the curvature of D. And equating the 2 field strengths like this gives you a dual description of the theory. So let's talk a bit more about this dual graviton, capital D. So it turns out that to describe the same number of degrees of freedom as H in arbitrary dimensions, D has 2 different types of gauge transformations. So some of them are controlled by this tensor zeta, which is a d-4, 1 type tensor, and the other type is a d-3 form phi parameter. So a natural object to define then, much like we had the connection for the graviton, is this dual connection, which is 1 skewed derivative on D. And so if we study in the dual theory, shift symmetry of D by some parameter alpha tilde, which obeys, again, a particular flatness constraint, the Ricci tensor built out of alpha tilde is 0, or the analog of the Ricci tensor in the dual graviton theory. Then this symmetry has a Noether current in the dual description, which has this particular form, and is conserved on the equations of motion when written in terms of the dual graviton. So if you think of this as a theory of the dual graviton, then you would call this electric. But we might want to interpret it back in the original graviton description. And it turns out that it's not so easy to do that because the duality fixes for us S in terms of R. It doesn't fix gamma in terms of gamma tilde. So recall S and R are both 2 derivatives on the gauge field, whereas gamma and gamma tilde are just 1 derivatives on the different gauge fields. But you can fix a gauge where the connections obey this relation, so-called duality gauge. And in that particular gauge, the current, which is associated with this shift symmetry of the dual graviton, precisely matches that one, which was the magnetic symmetry for the graviton that I wrote down. So what I wrote down before is just stating this is the current that you should consider. And the reason why is that you should really interpret it as the current associated with a dual shift symmetry of the dual graviton. Good. So the magnetic symmetry of H is an electric symmetry of D. Okay, so now we play the same game as before. We ask, do these symmetries have Hooft anomalies? And we should find how to couple background gauge fields. This time it's slightly more non-trivial. So the 1-1 symmetry was a shift of H. We can gauge it by introducing a gauge field in the 2-1 representation, and it transforms in this manner. So it looks very analogous to standard gauge field that we had before, but it transforms with a DL. Okay, and if I do that, then I note that the combination capital gamma minus C is invariant under the shift because capital gamma was DL of H, so it shifts by DL of alpha. So does C, so they cancel. So this little gamma is invariant. And then I gauge the action in the obvious way by just replacing capital gamma by lowercase gamma. Good. Okay, we also had the dual symmetry. And in this case, we can gauge it in the following manner by introducing a gauge field C tilde in the D-2-1 representation with, again, a standard gauge transformation of this form. And much like the magnetic symmetry for Maxwell theory, we gauge it by adding a term to the action I've written it in this way to make it look like what we wrote for Maxwell theory. So recall for Maxwell theory, this was F wedge B tilde. Here I've written gamma wedge dot C tilde. This term is exactly equal to just the contraction between the current J tilde and the background field C tilde. So again, it's the standard Noether type coupling that you would want to write down. This wedge dot is a wedge on the first sets of indices of the two objects and a dot on the second set of indices of the two objects. Good. So we've shown then that the symmetries on their own do not have Hooft anomalies. I've coupled background fields and made the actions invariant. But we should ask again whether there's a mixed Hooft anomaly. So we try gauging both. So the naive thing to do is just to combine both the ingredients above. We replace capital gamma by little gamma, and then we add this other term. And you'll find it works precisely the same as for Maxwell theory that we did before. So the magnetic type symmetry is invariant. So the action is invariant under those transformations for the magnetic symmetry, but not for the electric one. You can try and fix this by replacing capital gamma by lowercase gamma in the second term, and then you're guaranteed to be invariant under the 1, the shift of H, but you lose invariance under the magnetic symmetry. Good. So this is, again, exactly the same as it was for Maxwell, just with a slightly more complex set of indices. And again, you can convince yourself that there's no way to couple the background fields, which will simultaneously couple both symmetries in a gauge invariant way. And so we've derived a mixed Hooft anomaly between these pairs of biform symmetries. Good. So for the spin 1 case at this point, what we did was study a correlator between the two currents, roughly speaking. And we fixed its form by using the Ward identities that came from this Hooft anomaly. So we might want to do the same thing in the graviton theory and study this correlator, but that's obviously a non-starter because neither J nor J tilde is gauge invariant. So this correlator it has no well-defined form, so I'm obviously not going to be able to fix its form. So instead, we should find a correlator that we can fix. You can do that in the following way. If you take derivatives of J and J tilde and skew them in the right way, you can build a pair of objects, which I've called X and Y, which are gauge invariant. Okay, they are if you plug in what I told you J and J tilde were before, you'll find that in fact they're proportional to the Riemann tensor and the dual of the Riemann tensor on its first set of indices. And furthermore, the conservation of J and J tilde, if you use those in these equations, you will find that X and Y are also conserved on Sharp. Good. So X and Y are gauge invariant operators which are conserved, and we could try and fix their correlator. So let's do that. So start with the theory where I've gauged the shift symmetry of H. This is what we did before. In that theory, these X and Y are not gauge invariant objects because they depend on gamma, and gamma varies if I do this shift. So instead, I should replace gamma by gamma minus C. I build these bold objects which are gauge invariant. They're well defined in the gauge theory. And just like before, we find that while the one corresponding to the electric symmetry is still conserved, the one corresponding to the magnetic symmetry is not. Okay, so again, gauging the shift symmetry of the graviton breaks the magnetic symmetry. There's an extra piece of information that you have in this case as compared to Maxwell theory, which is the fact that the trace of X, remember X is proportional to the Riemann tensor, so its trace is just a Ricci tensor, that is 0 on the field equations in the original theory. But once I do the gauging and look at this improved bold X, then there's a contribution to its trace from the background field as well. So I now have 3 pieces of information. But you can play the same game. You try and impose them simultaneously in the quantum theory as Ward identities. You take functional derivatives with respect to the background field, and you fix the form of a correlator. Correlator in question is, again, the correlator between the two currents. So I look at the correlator between X and Y, and I write it in momentum space. I'm not going to write out all the terms that come up in the most general Lorentz covariant form that this can take. There are many of them. I think there's 11. Nevertheless, you write down and then you roll up your sleeves and you impose these Ward identities from the previous slide, and you will find that you can fix the form of this correlator up to contact terms. And the form that it takes has indeed a pole as p squared goes to 0. And so you can derive the presence of a massless mode just from this anomaly. The same comments that I made before apply. If I change the way that I gauge and couple these background fields, then I can affect the contact terms that appear, but I can't affect the structure of this pole. Okay. And again, you can apply these arguments about representation theory to show that the resulting massless mode is spin 2. Good. So that takes us to the main conclusion, which is that the graviton should be seen also as a Goldstone type mode. It's massless because of a mixed Hooft anomaly, and the symmetries that are involved in this mixed Hooft anomaly can be interpreted as a shift of H and a shift of the dual graviton D. Okay, so again, I started here with the free graviton theory and then derived the existence of a graviton, which is hardly impressive, but the point is that the existence of the graviton followed only from the anomaly structure. So these ward identities implied its existence, and so any theory with these symmetries would have such arguments. And in particular, you can deform the graviton theory in such a way that preserves the symmetries. Good. An important comment is that the nonlinearities of the Einstein-Hilbert action are not of this form, and they break the shift symmetry. So seen from the perspective of GR, then this shift symmetry, which plays a role here, is only emergent in the linearized limit. Good. I should also comment on work that appeared previously in the literature. They considered a smaller shift symmetry by a parameter which is the divergence of some 2-1 tensor lambda. This is a useful thing to consider because if you do that, then the Noether current itself is the Riemann tensor. So then you don't have to go through this the complications of having Noether currents which aren't gauge invariant. So the issues of gauge invariance are definitely simpler, but notably the gauging is much harder, and there's an impressive calculation in this paper explaining how to gauge these symmetries. Nevertheless, I think the fact that the graviton can be explained as a Goldstone associated to the most general shift symmetry of H is what one would expect normally for Goldstone modes. So I think it's gratifying to see it in this way. So I have some slides on other symmetries of the spin 2 theory, but I think I'll skip through them quickly and conclude. And if anyone is interested, feel free to ask me afterwards. Otherwise, I'll end up going over. Good. So we discussed global symmetries and their role in general in constraining RG flows, particularly through any Hooft anomalies that they might have. I demonstrated a pair of cases where there are dual symmetries that are generalized symmetries, higher form ones and biform ones, which have mixed Hooft anomalies. And the presence of these Hooft anomalies can be used to derive the fact that there is a gapless mode in the spectrum. So you can see the photon as a Goldstone mode protected by an anomaly between a 1 form and D-3 form symmetry, and the graviton is a Goldstone mode resulting from a similar mixed Hooft anomaly between a shift symmetry of H and a shift symmetry of its dual. So a key ingredient in the discussion is a set of dualities that these tensor gauge theories have. And so what I didn't tell you, but we'll be happy to discuss, is a larger set of symmetries that the spin 2 theory has, and they can be used to encode in a gauge invariant manner the ADM charges and a further set of magnetic charges. So some future directions, it seems obvious to try and make similar deductions on other backgrounds that aren't just flat space for the graviton theory. And more in relation to this final point here about the other set of higher form symmetries, these appear to have a very natural analog in full nonlinear GR, and so it would be interesting to revisit those in the context of some work by Castor and Trasher in particular, and try and learn something new about symmetries of solutions of full GR, given the intuition from the linearized theory that I've presented. Okay, thank you very much. That's all I have planned.
Thank you, Max. Any questions? So maybe you can quickly skim through, just tell us about this symmetries that you skipped.
Yeah, sure. Very good. So the obvious downside of the symmetries that I discussed is that the currents aren't gauge invariant. And another downside is that they are also not fully antisymmetric. And so if you have a tensor that isn't fully antisymmetric, there's no natural notion of an integral of that object in a way that's coordinate independent. So So one thing that you can do to fix both of those problems is consider currents that are built out of the linearized Riemann tensor, because it's gauge invariant, and you can contract two of its indices away with a two-form. So the resulting object is a two-form and it's gauge invariant. And then if you demand that this object is conserved, then it puts some constraints on K. In particular, K will have to solve this equation, which is known as the conformal Kilignano equation. And on flat space, there are many solutions, and you can write them down explicitly. But for each solution, you can then integrate the Hodge dual of this current then over a codimension 2 cycle and build a symmetry, a charge Q, which is a topological operator, again, in the sense that I can deform sigma, and Q will not change. Good. So there's quite a rich set of these symmetries, and they have some very interesting properties. Firstly, they come in 4 types. So on flat space, the most general solution of this conformal Kilignano equation takes this form. There's one term which is just a constant 2 form. There are 2 types of contributions which are linear in the Cartesian coordinates of the Minkowski space, and there's one term which is quadratic. So this is the obvious sort of second rank generalization of a conformal Killing vector. Good. So it turns out that they are the nature of these charges depends heavily on the dimension of spacetime. So in 4 dimensions, there's a special case where all 4 ABCD types of these symmetries give non-vanishing charges. But in greater than 4, the A and C type charges become trivial. What happens is the currents become co-exact. And so when you integrate them over a cycle, the result vanishes. And so in fact, a load of them disappear in higher dimensions, and you're left with only the B and D type charges. You can also study mixed Hooft anomalies between these symmetries, and it's very non-trivial to find the correct coupling of the background fields. But nevertheless, what you find is that all of them can be coupled on their own, but there are specific pairs of them that cannot be simultaneously gauged. So a general pair of them will have no mixed Hooft anomaly, but there are specific pairs which do have mixed anomalies. So there's a very sort of subtle and rich structure of these symmetries. They also have a very interesting interpretation in the following way. So the ADM charges can be seen to arise in the following manner. If you consider a gauge transformation of the graviton and choose the parameter to be a Killing vector of the Minkowski space, then the gauge transformation itself will vanish. And so this gives an invariance of any configuration of the field. And that should be seen as a global symmetry. And there's an associated conserved 2 form, which happens to take this form. The only thing that I want you to note about this form is that it depends in this term on 1 derivative of h, and in this term on no derivatives of h. So this is definitely not a gauge invariant object. And so the charge that you build from it as a result is in general not gauge invariant. So that as you do a gauge transformation, it varies by a total derivative, but it is a total derivative of something that is not covariant. And the fact that it needs to be patched together means that it's sensitive to topological features of the gauge field. So in particular, when the gauge field has non-trivial topology, this is not a gauge invariant charge. But you can relate them to these conformal Kilignano tensor type charges that I discussed above by noting that on Minkowski space, any Killing vector can actually be written as the divergence of one of these conformal Kilignano 2 forms. And with that knowledge, you can massage this 2-form current J of K here and show that the charges associated with the conformal Kilignano tensors give you the same charges that are associated with the Killing vectors. So these are the linearized ADM charges, up to a surface term. And importantly, this surface term, again, this Z is not a gauge invariant function of H. So what happens is if I look at a configuration where H it has trivial topology, so for example, a linearized Schwarzschild type solution, then this final term vanishes. It genuinely becomes a surface term, and when integrated over a cycle, it vanishes. And I just find that the ADM charges are given by these conformal Kilignano type charges. But in general, if I have non-trivial topology, then this second term will contribute, and you should see these conformal Kilignano charges as giving you a gauge invariant improvement of the standard ADM charges. So you can see a similar thing from the dual theory. So again, D has this much more annoying gauge transformation, which comes in 2 different types. And if you consider parameters for the gauge transformation, for example, set zeta equal to kappa, where kappa solves this equation, and set phi equal to lambda, where lambda solves this equation, then again you get invariances of the dual graviton. So these play the role of the killing vectors, but in the dual theory, so they're normally called generalized killing tensors in any case. And again, just like for the graviton theory, there are some two-form currents which are associated with them. And so you can analyze these in the dual theory, and you can furthermore try and write them back in terms of the graviton. Because they arise as electric charges in the dual theory, they should be seen as magnetic charges for the graviton. So there was a nice paper from Chris Hull about a year and a half ago discussing these charges in the graviton theory and how they are the correct charges to measure, for example, the charges of Kaluza-Klein monopoles and Taub-Nut type solutions. There's also a link of these charges to the conformal killing Yarnow tensors, because all solutions of this equation on flat space for lambda happen to be able to be written as the form star dk for a conformal killing Yarnow tensor k. So if you use this knowledge, you can take the explicit form of this j of lambda, which I haven't written down because it really is awful, but you can massage it and you can again find a similar relation, showing that the conformal killing Yarnow tensor charges should be seen as a gauge invariant improvement of these charges associated with the lambdas. So I didn't mention the kappas. A similar story applies. There's a slightly more general setup that you need to consider, which I can discuss if anyone wants. But the point is that all of the naive Noether charges associated with the killing vector invariances of the graviton, and both of these types, lambda and kappa invariances of the dual graviton, can actually be seen as coming from these more general charges associated with conformal killing Yarnow tensors.
You mentioned that there is difference between 4D and higher D. Can you elaborate a bit more on that?
Yeah, so there's an interesting. It's largely a coincidence. What you find that you can. So for the A and C type Ks, conformal killing Yarnow two forms, they are in fact so they're co-closed. This A and C type solution, but furthermore they're co-exact. You can actually write down a three form which these are the divergence of, and if you use that fact, you can show that the current y, if you know that K is the divergence of some three form, y itself can actually be written as the divergence of a three form, and that three form depends on the Riemann tensor R. And so if you know that y itself is co-exact, then if I'm integrating its Hodge joule over a cycle, then it vanishes by Stokes. So that's the sort of mechanism by which it happens. The same isn't true for the B and the D because they're not co-exact. But yeah, so it happens that in 4D, the comments that I made would be true, but the three form which this two form current y of k would be a divergence of vanishes identically. So in 4D, by a happy coincidence involving the Bianchi identity, you get these contributions as well, but they vanish in higher dimensions. So it's important because there are some. So this paper has a nice discussion that there are some grounds to believe that higher form symmetries should always come in dual pair, continuous ones should come in dual pairs. And so in particular, you should have the same number of one form and d-3 form symmetries. So we saw that in the Maxwell theory, you had F and star F, and in the graviton theory, you had this J and J tilde. And here I'm saying there's a whole set of one form symmetries that these Q are generating. So you can ask, okay, what are the d-3 form symmetries? And so the objects to consider would be the Hodge jewels of these Ys, they're d-2 forms, and you ask when are they conserved? And you find that they're actually not, so in 4 dimensions, they're conserved for any conformal killing Yarnow tensor K. But in more than 4 dimensions, only half of the Ks give you a conserved dual object. And so if this expectation that there should be the same number of one form and d-3 form symmetries is to be true, then you should find that some of the one form symmetries are in fact not there, and that they're trivial. And so that's really what's happening, is that these A and C type ones have to be trivial in more than 4 dimensions, such that you always have the same number of one form and d-3 form symmetries.
Oh, I see. So in 4D, it happens that you have different number.
So in 4D, it's true that Y is both conserved and its Hodge joule is conserved for all of the Ks. So you could say that there are 20 charges of this form and there are 20 dual charges. Actually, it turns out that the dual charges can be written as a linear combination of the original charges. So actually, there are only 20 independent ones open.
Okay. Yes. There is also this other issue, which is not directly related, but I wonder if you have anything to say. So when you describe graviton as a dual, then it's a mixed symmetry form, right? It has two different symmetries that you showed of different tensor type. And these two different symmetries are not always possible to realize simultaneously. Only in the flat background you can, but if you are in a curved background, then you cannot. So
that's definitely true. Yeah.
So
I think that's one reason to think. So what I was meaning to say in the conclusion is that if you look at this type of object here, there's an obvious curved space generalization, which is to take the full Riemann tensor, not just the linearized one, and take a conformal Kilignano 2 form on the full solution curved space that you're looking at. Because if you focus on these charges, like you're saying, these charges that are associated with the particular form of the gauge transformation of the dual graviton, then you immediately have to give up on them as soon as you move away from flat space. Even if you, I mean, this is some of your work, but even if you go to ADS or to Sitter, which supposedly should be the easiest targets, you can't simultaneously have both of these gauge transformations. So you would then give up on these lambda and kappa type charges. But it seems obvious that the ones relating to the conformal Kilignano tensors, because they just depend on the Riemann tensor, should be present in both cases. And so the particular example of ADS and DS admit the same number of conformal Kilignano tensors as flat space, so you can very explicitly construct these charges there as well.
Thanks.
Can I just make one comment?
Please.
Sure.
Yes. Well, it's more a suggestion that one thing that you might want to do, as Max said, is make this study the equivalent situation in nonlinear theories. Another one would be to look at fermionic symmetries, and in principle, some of this should be possible to embed in a flat superspace description. There are, for example, super conformal Kilignano tensors, which has mixed bosonic and fermionic indices that might come in useful. And it's also, and there are also relations to killing spinners that you might want to use. So I suggest that looking at that might be fruitful.
I agree. I think that would be an interesting thing to consider. I think there's recent work as well by Thomas Ogtin and collaborators about generalized Komar type charges in superspace and that type of argument that I think is possibly related. So it would be interesting to just to find some sort of connection there.
Yeah.
Maybe we can conclude the official part.